Hi, welcome to College Algebra, section 3.2. We're going to start looking at polynomials with higher powers in them. Okay, so up to this point, you've probably done a fair bit with things that have, say, x squared in them, but maybe not as much with something that has, x to the fifth. So we're going to be looking at bigger polynomials. They're going to be kind of fun. I really like them. And so let's get started. The first thing we need to talk about is what's called end behavior. So it's important to know that end behavior only cares about what happens on the graph as you go really far out to the left and to the right. End behavior doesn't care at all about the middle of the graph. That's something we'll deal with a little bit later. But end behavior deals with, again, what happens as you go really far out to the left and the right. Basically, what we in math would be as x goes to negative infinity or as x goes to positive infinity. All right, so let's take a look at what end behavior does. So first of all, we're going to be looking at a generic polynomial. I have one written on the board here. F of x is equal to a sub n, x to the n plus, and then a lot of dots, all the way down to a sub 1x plus a sub 0. Basically, the n is just the highest power of this polynomial, and then we have coefficients for all the terms. Okay, and we're calling them a sub n and a sub n minus 1 all the way down till we run out. And it's just a nice generic way to think about a polynomial. So if n is even, okay, if your highest power is even, two possibilities. If that leading coefficient is bigger than 0, then it's going to act just like a parabola. On the ends, it's going to go up in both directions. In math, we would say that as the function f of x goes to infinity as x goes to either positive or negative infinity. For a sub n less than 0, we would say that f of x. So what that does is it's just going to flip it upside down. If you think about the transformations of graphs that we did before in chapter 2, a negative multiplying by that is going to flip it upside down, and that's all that's going to happen here with that parabola. But we would say that f of x goes to, this should be negative infinity. Oh my, that was bad. There we go. Negative infinity as x goes to positive or negative infinity. Now, if n is odd, it's going to act more like a third degree polynomial. So you have this nice kind of cubic shape, I guess, and that's what odd ones are going to do. Notice that for these, it's going to go in different directions. On one side, it'll be up, and on one side, it'll be down. So if a sub n is bigger than 0, again, if that leading coefficient is positive, it'll actually end up looking just like that on the ends. So we would say that f of x goes to negative infinity, the function goes down, in other words, as x goes to negative infinity, and we would say the function goes to positive infinity as x goes to positive infinity. And all that's reversed if you make the coefficient negative. Now it goes to positive infinity as x goes to negative infinity, and the function goes to negative infinity as x goes to positive infinity. So that's end behavior. We'll look at an example here and then we'll move on, but I need some new stuff on my board, so give me just a second. All right, so I have an example here for end behavior. We're going to describe the end behavior. My function is negative 3x to the fifth plus 7x to the fourth minus 3x cubed plus 1. So the only part that matters is that first term. The rest of it we don't even care about. So what I notice is that the highest power is odd. It has a negative coefficient. So I know this will act like a third degree polynomial, but it's going to be flipped upside down because of the negative. So that tells me that as x goes to negative infinity, as we move out to the left on the graph, the function is going to go up. And as we go out to positive infinity, as we go out to the right, the function will go down. And that's really all there is to end behavior. So you should be able to describe that to me. That would be great, and you'll get some practice in the homework. All right, relative maxes and mins. This is not the biggest, most important topic, but I did want to look at it a little bit. There's a lot of really good stuff that I'm going to just kind of really quickly go through with your calculators. So what I'm looking at here, a relative max is basically a high point on the graph, and a relative min is a low point on the graph. Unfortunately, to really do a very adequate job of finding them algebraically requires calculus. And if you're watching this video, you probably haven't taken calculus yet. Okay? I mean, maybe you have, but probably not. Right? This is a course that comes before calculus. So we're not going to find these algebraically. But what you can do is if you put in the equation into your y equals menu, on your, so I'm using a TI-83, into your calculator. If you type it into that y equals menu, then if you look up above trace, it says calculate, or it says calc. But so you hit second trace, and when you do that, you get a whole list of really neat things. And so I'll let you, here's mine, but notice that down there at numbers 3 and 4 are minimum and maximum. So I would encourage you to mess around with those a little bit. Actually, probably the most important one for the things that we do is actually number 2, zeros. Because we will use our calculator to help us find zeros for these functions eventually. But that's a story for another day. So anyway, those are relative maximums and minimums, and you're really going to, at this point, find them with your calculator because it's not something we can do algebraically, at least not yet. All right, so a couple of last things. Oh, well, evidently I forgot to pause my video, so you've watched me right on the board for the last 2 minutes. Sorry about that. Hopefully you skipped ahead because that would be a waste of your time. All right, and unfortunately, I don't know how to video edit. You get what I record, so sorry about that. All right, anyway, finding zeros. You have two options. You can either factor the polynomial if you can, or you can use your calculator. So factoring, hopefully you already know how to do that. I'm not going to cover that here. That definitely is something you should have figured out before you got to this class. If you need help with it, go back. I have actually videos for introductory algebra where I teach factoring. So you can go back and find those if you really wanted. Or you can use your calculator. So this is what I just talked about. That is a button on your calculator. You can type it into your graphing menu. You get to put in your function, hit second trace to get to into that calculate menu and pick 0. You do that, and then you follow the directions to try and find zeros. And that's an option. We will have better options here coming in the next few sections. But for now, that's really all we have. All right, so we do have to talk about one more thing before we kind of just throw it all together and talk about graphs. Multiplicity. Multiplicity of zeros, these are repeated zeros. There are zeros that happen more than once, and you're like, well, that doesn't really make any sense. If 2 is 0, how can 2 be a 0 more than once? It's already there. Well, we'll do an example here, and I'll kind of point it out. But just let's go trusting me for just like 30 seconds until I get there. They are repeated zeros. If it's an even power on that repeated 0, it's going to touch the x-axis but not cross. If that is odd, you will pass through the x-axis. So let's go ahead and get an example on the board and we'll take a look at it. And we'll kind of talk about graphing here all at once. It's going to be super fun. All right, so I have the things that we need when we're making graphs of polynomials on the board, and then I've started an example of graphing one, and I'll finish it up here as the conclusion to our video. So here's what we need. We need to know what the end behavior is. We need a y-intercept. That's always nice. A y-intercept always happens when x is equal to 0, so just plug in 0 for x. Always a very happy thing. 3, the x-intercept with multiplicities. For that, we're going to set y equal to 0, or rather, the function will be set equal to 0. So I've really kind of shortened this problem out that I have here, but I'm going to talk you through it just a little bit. I have p of x is equal to x plus 3 squared times x minus 1 to the third power. All right, so first thing I need to know is that the highest power here is going to be 5. I'm getting that from the 2 and the 3 for those exponents. And because these are both just x's that have positive numbers in front of them, they both have a 1 in front, it's going to be end behavior that will be down on the left and up on the right because this is an odd power with a positive coefficient. Okay? You don't actually have to multiply this out. Please don't. All right, so I have the end behavior, and I kind of marked it on the graph. I want to know, okay, this is where it's going to start, and this is where it's going to end. Next, I found the y-intercept, and I actually did the work over here. I have p of 0, so notice, I'm plugging in 0 for x, and I kind of cheated just a little bit, so hopefully you follow along, but I plugged in 0. 0 and 3 makes 3, so I had 3 squared. 0 minus 1 is negative 1, so I had negative 1 to the third, and if you multiply that out, you get negative 9. So notice I have a point down here on the y-axis at negative 9. Finally, I need any x-intercepts with their multiplicities. So this is kind of the most important bit maybe, because this is probably new. So to do this, I would set the whole thing equal to 0, and I hope you can see, but if I do that, the negative 3 is going to be a 0, because if I plug that in here, that'll make this first set of parentheses 0, so I have negative 3 marked on my graph, and the same thing with positive 1. Okay, so since this is already factored, whatever makes 0 for the parentheses will actually be a 0 on my graph. All right, so here's where the multiplicity comes in. I know that at negative 3, its multiplicity is 2. That's an even multiplicity. If you remember from the last board that we said that when you have an even multiplicity, you touch the point, but you don't actually cross through it. And that's actually good because we need to get down to this point, and so there's not going to be any way to do that. And so then we keep coming, and we get back to this other 0, and at 1, it has a multiplicity of 3. So with a multiplicity of 3, it's going to cross the x-axis, and it's going to continue up, and that's good because then it matches my end behavior, and I get what's really a pretty rough sketch, and that's okay. I don't need perfect graphs, but I do need these characteristics. But notice that the multiplicity tells us, how to get all the way through these points, because maybe, if we mess it up, we go through this point, and then it's impossible to get down to there. But the multiplicity helps. So anyway, take that into consideration when you're making your graphs, and good luck.